Welcome to another Taz Academy HVAC training video. Do's and don'ts of duct fittings. Why good duct fitting choices are the best thing you can do for your duct design. I am your host, Randall S. Ripley, Technical Support Manager and Trainer at Total Air Supply, a Marcone company. Do's and don'ts of duct fittings. In the Ductulator video we put out last week, I briefly touched on duct fittings, and I said that making good fittings choices are the best thing you could do for your duct design. I also said with a low friction rate, one faulty component can severely hamper airflow because there is less room for error. In this video, we will go into depth about why your duct fitting choices matter. Just two things in your ducts are responsible for giving the blower in your furnace or air handler a hard time. They make the blower push against more pressure, thus reducing airflow or increasing energy use, depending on the blower type. They cut the amount of air that gets delivered to the rooms, and they can be reduced but not eliminated. Do you know what they are? The first cause of reduced airflow is friction. When air moving through a duct rubs against the inner surface of that duct, it loses energy. It slows down. Its pressure drops. The more it rubs, the more those things happen. It's like walking down a busy sidewalk with your shoulder rubbing against the building. The amount of friction depends on the nature of the material the duct is made of, how it was installed, how dirty it is, and how fast the air is moving. And we all know that flexible duct, when it's installed straight and pulled tight, is quite good. But when it looks like a snake like this up in the attic, which, in attics, they don't get pulled tight or anything else, they're bent over the beams or whatever, and it crushes the flex duct. And, that's why we use sheet metal a lot of the time, because the smoother inside creates less friction than the old pan bays everyone used to do. A lot of municipalities don't allow now. They were wood on the sides and stuff. And of course, that was more friction. And pan bays didn't carry as much airflow as people thought they did. The other primary cause of reduced airflow is turbulence. This one is a kind of friction of the air rubbing against itself. The main cause of turbulence within ducts is turning the air. When you see air through send air through a 90-degree turn, the type of fitting you use to do so can make a big difference. And we see here, when it's a rounded throat and a rounded heel, we have a lot less turbulence, a little bit built up here, whereas when we have a square throat, there's more turbulence, and it creates less airflow because you've got a restriction here of this airflow, of this eddy currents here. And the same here, when you use a square fitting and all the air just comes up and beats across the top here and then kind of like staggers out in the airflow, and you see you've still got all your little eddy currents down here too. So airflow, the more rounded, a rounded heel is good, but it really matters is here on the throat. So we have laminar flow and turbulent flow, and we see here Hang on just a minute, folks. I want to get my pointer. There we go. So we see laminar flow and turbulent flow. And laminar flow is, a smooth flow where the airflow layers, represented by the arrows, they do not mix. And they will glide over each other, and that will be good. But we see here in turbulent flow, like here and over here, that the fluid layers mix, and the velocity, temperature, mass concentration at any point can vary. But we need to have good, smooth airflow, and that's what picking your fittings types and the equivalent lengths, as we're going to talk about again here in a minute, that's why picking your fittings is so important. And picking right fittings, of more rounded elbows rather than square-throated elbows. Or, some elbows even have square heels as well. Airflow wants to move in the path of least resistance, which is straight down the duct. It will not turn unless you help it. And in this return, we see here what is basically a square throat and square heeled fitting of our return. And if we look at that, we see that over here on the heel portion, we do have some eddy currents, and over here on this side. But we look up here again, that square throat caused a lot of turbulence air right here on that, right off the throat, so that we're not getting as much flow because we see the flow here. And we actually have a video coming up that shows this phenomenon, or whatever it is, in the ductwork. So, but just keep that in mind. When you have a square heel and a square throat, you're really restricting your flow. And on returns, that's almost a given that's how guys are going to do the return. And again, we see here pour, and here's our return drop here, and just squared off, square throat, square heel. Good. We're trying to round the throat a little bit and round the heel a little bit. And then better, put it on a return base here. I'll put the air handler or furnace on top of the, a return air box, and then do a 90 rounded throat and rounded heel 90 into it. So what causes the air to come out of the diffusers? When you get airflow from your diffusers, it is because the air pressure goes to the end of the duct, hits the wall, and cannot go any further. And remember, up here on our duct, we leave that last foot 18 inches to 2 feet without any takeoffs, for that reason, to create that back pressure, for it to hit it, and that creates a pressure buildup from the end of the trunk back towards the plenum. The path of least resistance is now your diffusers. There is a lower pressure outside the diffusers than inside the ductwork. And high pressure flows to low pressure always. Every duct fitting and connection you use has an associated equivalent length. ACCA's Manual D for duct design has tables of equivalent lengths for all kinds of duct fittings. Study the tables and avoid the fittings with high equivalent lengths when possible. The equivalent length is often forgotten and can have huge impact on design and performance of the fitting. Equivalent length compares a duct fitting to what its length would be if it were straight. It also describes the amount of pressure loss in a duct fitting that would be comparable to a length of straight duct. Accurate measurement is required to get proper sizing of ductwork. We need our linear lengths accurately measured. Effective length of the duct run is shown here, but it also includes all the equivalent lengths of the fittings. So just remember that, when you see the term effective length, it includes all this linear footage and then the equivalent lengths of all fittings in that run. Like here, it would be this takeoff here, then the length. This takeoff has an equivalent length. This top takeoff, the boot, they all have equivalent lengths. And again, effective length is the sum of the actual measured length of the duct plus all the equivalent lengths of the various fittings included in the duct run. And here's the bottom line. Duct fittings with sharp turns have higher equivalent lengths than fittings with gradual, smooth turns. Bad fitting choices and/or undersized ducts choke airflow. Just to reiterate how important a rounded throat is on a turn, let's look at the following example. A 90-degree elbow with a square throat, round heel, and no turning vanes that is 24 inches wide has an equivalent length of 100 feet of straight duct. That same 90-degree elbow with a rounded throat and heel and no turning vanes that is 24 inches wide has an equivalent length of 20 feet of straight duct. So if you're, that right there alone takes up, a lot of your airflow when you size at the 0.10 as we talked about in the last video. So really picking the right duct fittings, you want to make sure that even boots, angle boots and top takeoffs, there's better ones with better equivalent lengths than others. So you see that one fitting is a big hit to your effective length, and that's where they're saying, that's saying of, with low friction rate, one fitting can blow up your duct design. Here's the video of the test. It's an old video. The volume isn't that good. You might have to turn your volume up a little bit. But I just wanted to put this in here because it actually shows the air currents. So I hope you're patient, and if you don't hear it that well, at least you get to see the airflows.
Now let's examine how duct design and installation can affect fan performance. Normally, a fan is tested with an open inlet and a section of straight duct attached to the outlet. This setup results in uniform airflow into the fan and efficient static pressure recovery on the fan outlet. To observe the movement of air molecules in the duct, we've introduced helium-filled bubbles into the airstream. When space constraints do not allow for a section of straight duct, an elbow must be placed near the fan outlet. But look what happens. This installation results in an abrupt change in direction of airflow. It causes turbulence within the fitting. One bad connection can reduce airflow significantly below the fan's catalog performance. To calculate airflow in the duct, we've installed an airflow measuring station. This duct configuration is a reproduction of a test setup from AMCA Standard 210. Unrestricted, this fan delivers just over 1,800 CFM. Now we'll add an elbow to the duct. Notice the turbulence within the fitting. It causes significant pressure drop. In this example, simply by adding one elbow to the system, airflow has been reduced approximately 25%. One way to improve the efficiency of air movement through the fitting is to install turning vanes in the elbow. The airflow is less turbulent and more uniform at the discharge of the fitting, resulting in a lower pressure drop. In this case, the airflow has only been reduced about 6% from the fan's initial performance. Many designers prefer utilizing radius elbows. In this test, this is the most efficient fitting of the three. The reduction in airflow is less than 4%. Remember, as originally tested with an open inlet, this fan delivered just over 1,800 CFM.
Because air wants to travel in the path of least resistance, if you want it to turn, you need to help it do so, as we saw in the video. So we look up at this video, again, square throat, square heel. It's inefficient. And then we have efficiency over here. The turning vanes, remember we lost 25%, then it was about 7. So with the turning vanes, excuse me, turning vanes can help, but turning vanes should only be used on low velocity systems where radius elbows will not fit. So if you can't fit a radius elbow in there and you need to use a square one to get it in there, well then I guess you use turning vanes in it and call it good. But use radius elbows wherever possible. And as we said, sharp turns in duct systems effectively reduce the size of an opening when air attempts a 90-degree turn. As air tries to go around a sharp turn, a tremendous amount of turbulence is created and airspeed decreases, as we saw in the video. And always use radius elbows rather than square elbows whenever you can. And here we just see more of different types of fittings. We see a sharp angle here. We see eddy currents, and that has a square heel, but even on this one with a rounded heel, we still see we get eddy currents on the square portion of the throat on both of these. And then, of course, rounded elbow, corners help, or long radius bends. And here we have turning vanes, and splitters. So, those are better choices, everything rounded, throat and heel, long radius, anything that helps that air turn versus resist the air turning. And here we see square heel, square throat, poor choice. This one's better because it has the turning vanes in it. And best, obviously, is radius with a rounded heel and a rounded throat. Again, a choice here. We have to remember we'll get a little bit of pressure out of a fitting like this, but we're not going to get a lot. A little bit better is that we add a little extra angle, like 50% more, and that creates more of a low pressure outlet and allows air to flow out more freely. And then, of course, something like this is the best option for doing that if you need to take a duct off the side or something of that sort. Deadhead plenums or bullhead T's leave air with no direction as it exits a furnace. Air ends up splattering into the end of the duct, creating turbulent airflow. So we know that where this is square, we're going to have turbulence, but also all that air is just coming straight up off that blower motor. It's just deadheading here and then kind of like staggers out and goes down the duct. Same with the bullhead T. All the air, because remember you're blower in your air handler is blowing straight up, or furnace is blowing straight up. So it's going to hit all this and then stagger on down through. So Bullhead T is poor. At least this with rounded throat is better. You have turning vanes here, that's even better, and this is what's best, something that splits it. So don't use Bullhead T's. If you install an elbow or Bullhead T near the discharge of the blower, you will create turbulence inside the duct. That creates heat transfer out of the duct, making it cooler. Air turbulence inside ducts can affect the R value of the duct insulation. In some cases, this can make the difference between duct sweating and not sweating. Adding turning vanes inside the fitting can fix this problem and increase airflow as well. Use fitting with turns that move the air through the changes in direction smoothly if turning vanes are not used. And there we're using, see, we're splitting it here. And, if you're going to come out like this on a duct, this is the better way to do it anyway. The blower motor is mounted so that it's blowing the air straight up. We know that the blower comes up and the air blows straight up. To assist the air in turning and flowing into the duct at a higher velocity, use a properly sized plenum with offset takeoffs that have an opening size approximately 50% larger than the duct. As we see here, we bring that down a little bit more. And over here, we see it on this here. And that's going to help us because, we have the 8 inches here, 12 inches to here, say, but that helps with create a better, guide that into that lower pressure zone. And, like I said, creates that merge. And if we look here, it shows one that doesn't have the offset and one that does. And we save 25 feet in equivalent length just by using these types of takeoffs versus just doing this kind of a regular 23 takeoff. Or, yeah, I think that's called a 23, but you know what I'm talking about. And again, transition collars, if you can't put, like, say you have a duct that's bigger than the plenum, so you extend the duct and cap it over here and just blow into the duct where it fits on the plenum. You can't do that because now you've reduced it to whatever size that you didn't cap off. So using a transition fitting that's 23 AT in Southwark will help you transition air into that duct that's a bigger size. And that lack of transitions is going to create turbulence and restriction in your duct system. And if more than one reducer is used, they must all be installed so that the reduction is on the same side. We all know that. You always put them in the same on the same side rather than put one way, one the other way. So temperature, pressure, and amount of volume of a gas are independent, and many scientists have developed laws to describe the relationship among them. Boyle's law is named after Robert Boyle, who first stated it in 1662. Boyle's law states that if temperature is held constant, volume and pressure have an inverse relationship. That is, as volume increases, pressure decreases. So that's why we can't have an abrupt expansion of airflow and then think we can go a certain amount of distance. So we need to change the duct size for whatever, and then go back to the other size on the other end. that's not going to work because of the pressure you're going to lose expanding into this duct, this larger duct. Increasing the amount of space available will allow the gas particles to spread farther apart, but this reduces the number of particles available to collide with the container, so pressure decreases. And then decreasing the volume of the container forces the particles to collide more often, so pressure increases. Good example of this is when you fill a tire with air. As more air goes in, the gas molecules get packed together, reducing their volume. As long as the temperature stays the same, the pressure increases, as we see in the two jars. When the cover's pulled up and when the cover's pushed down, this creates less volume, more pressure. This creates less pressure because the volume has to expand. And again, you can't have pressure losses. If you look at this, you can't have sudden contraction because of the pressure losses occur when abrupt contraction takes place. And we see that causes a vena contractor. It causes a vena contractor. And we see that this pressure, the larger amount, is pushing into this smaller opening. And it also creates dead space here. And that's the contraction. And then it gets over to here and it's expanding again. So that abrupt contraction is going to travel beyond the entrance to the smaller section, and that's going to drop that pressure. And that when that stream expands again in that smaller duct. And all that pressure loss is happening right here. And top takeoffs, even the different styles of top takeoffs have different equivalent lengths. Like this style of top takeoff, you see that it's rounded up here and helps bring everything right in. When you have the ones that have all the different pieces in it, like 3 or 4 pieces turning, those have higher equivalent lengths because they restrict air more. Use these offset type takeoffs to assist the airflow into the runout. And make sure all of these have balancing dampers if exposed. Thank you. If you like this video, please press the like button and subscribe to our YouTube channel so that you get all of the videos as they come out. Again, thanks for watching. And here's the address of our YouTube site. And that is my email address. And hopefully we will have you back for more videos. Thanks again.